I think we're going to finish with the sequences chapter. Finish with the sequences chapter this morning. You still have your tutorials this week where you'll still be dealing with some of the exercises from the sequences tutorial sheet. You may well still be working with some of them next week as well. There's a few things just a couple of things to finish off before we move on. I'm going to try and give an introduction to the series chapter at the end of this hour. So first of all, this is the handout I gave actually last week, and this was in order to finish off the algebra of limits theorem. Remember the algebra of limits theorem, which is at the bottom of page 6, top of page 7. This tells us how, when we take a pair of convergent sequences and put them together and form a new sequence in various ways, the new sequence is also convergent and it has the obvious kind of limit. So the first part was linear combinations. When you form a new sequence by essentially taking a multiple of an and adding it to some other fixed multiple of bn, that's the new term, that's the term in your new series. That new series will also be convergent, and it converges to alpha a plus beta b, where alpha and beta are the two coefficients in the linear combination. We also prove the product form. When you form a new sequence by multiplying together corresponding terms of your two starting sequences, then that new sequence is indeed convergent as well, and it converges to the obvious limit, just the product of the two limits. Okay? So the same operation that you're doing in constructing the new sequence, you're doing that, applying that same operation to the limits, and that's the limit for the new sequence. The part we didn't get to prove, and I left it with you for a week, and this guidance sheet to think about was the quotient form. So this here on the sheet is the statement of the quotient form. So we suppose we've got our two convergent sequences, an converging to a, bn converging to b. We want to prove that the sequence with these terms, so a1 over b1, first term, a2 over b2 is the second term, a3 over b3. This new sequence is also convergent, and it converges to a over b. Now, because we're messing around with b in the denominator placing a fraction here, we also need some extra non-zero conditions, okay? Because an over bn will never be defined if bn is ever equal to 0. So we insist that the sequence bn stays away from 0, and also that it isn't convergent to 0. We need to know that the limit is non-zero. So if the limit was 0, this fraction a over b would be undefined, and the quotient sequence wouldn't be convergent. Now, there was guidance of several steps here to get you thinking about how the proof of this is constructed, and I'm going to go through these now and answer these because I hope you give this a good try during the week. And you can still, this could be a subject of discussion in your tutorials as well this week or next week if you need to ask questions about it. So the guidance says, well, first of all, notice that we only have to prove a special case. Really, we only have to prove that 1 over bn converges to 1 over b. So the general form of an over en can be recovered by multiplying an by the sequence 1 over bn. That's taken care of by the product. I'll make some remarks about that. The second step was, well, writing down exactly what it is we have to prove. Writing down the formal definition of convergence but applied to our current situation. So given any epsilon, we will need to construct a point capital N such that this absolute value of differences, 1 over bn minus 1 over b, that absolute value is less than epsilon for every value of the index little n bigger than some point. We have to construct that some point capital N. We have to find that. That's what we have to do. And then, well, there's some guidance how to do this. The guidance is to consider the absolute value in this form here. So we're trying to make this quantity small, and this is where the detail is, and this is what I'll explain carefully. If you're trying to make a fraction small, there's kind of two components to it. In order to make a fraction small, you have to make the numerator small, but you have to make the denominator large. Okay? Because in a fraction, if the denominator is large, the whole fraction is small. But if the denominator gets very small, close to 0, then the whole fraction gets large. So if I'm trying to make this quantity smaller than epsilon, I have to control the size of the numerator, stop it getting too big, and I have to control the size of the denominator and stop it getting too small. So it's just a little bit of a technical, careful handling of what's going on there. Okay, so let's get to the proof of this, and we'll prove it by kind of following these stages here, answering these various questions. Okay, so at any point, if you want to stop me for further clarification, please do. Proof of the quotient form, theorem, what was it called, 1.4. So step 1, show that the theorem above can be derived from the product form of the algebra limits and the special case. So we will prove a special case. That Bn converging to B implies that 1 over Bn converges to 1 over B. Under the assumptions, assuming B is non-zero and for all n, Bn is non-zero. Okay, I won't keep writing those conditions down. Those conditions apply throughout the whole argument today. So that's a special case, because it's the special case where the sequence an is just a constant 1. Okay? But if, assuming this is true, we can combine this then with the product form. Well, you see, if I then have to prove that an over bn, what does that converge to? Well, I just have to notice that formally I can think of this as the quantity an multiplied by the quantity 1 over bn. But if I already know that 1 over bn converges to 1 over b, and an converges to a, applying the product form of the algebra theorem proved last week, I'll be able to conclude that this product converges to a times 1 over b, which is of course equal to a over b, as required by the statement of the quotient. So that's the argument for step 1. Okay? We don't actually have to go ahead and prove in detail this full version, that a over bn converges to a over b. All we have to do is prove the special case that 1 over bn converges to 1 over b, because once we have that special case, the general case can be got from combining it with the product. Okay? Because the quotient an over bn is equal to the product an times 1 over bn. So the special case tells me that 1 over bn converges to 1 over b. The assumption tells me that an converges to a. The product form of the algebra limits theorem, which we proved last week, tells me that the product of these two converges to the product of their limits, which is equal to a. Okay. So this is just settling, convincing us that we only need to deal in detail with this special case. Okay. Is that okay with everybody? Everybody need clarification. So this is often done in mathematics. Always be on the lookout for, getting away with it as little as possible. Mathematicians are lazy in a sense. So I don't need to go to the trouble of proving it for an over bn because the special case is enough when combined with something I've already. Okay. So now, well, step 2 is really just translating the general definition, the formal definition of convergence into this special case. So if we let epsilon greater than 0 be given, now we have to find, so this is what the work our proof has to do, we have to find point capital N such that I'm really only just copying out what's written there, just declaring it to myself. such that if little n is bigger than or equal to this point, capital N, then 1 over Bn, the distance between the sequence element and the limit, is less than that given epsilon. So remember, epsilon is a measure of closeness of the sequence element to the limit. And the point is we can do this for any sign, any measure of closeness, in particular smaller and smaller and smaller ones. For any measure of closeness epsilon, there is some point, capital N, after which our sequence elements, the distance between our sequence element and the limit, is less than that measure of closeness epsilon. Okay. But this is the all-important statement here. So this n, we don't know what this n is yet. Okay. The work we have to do is to give the recipe for constructing this point, capital N. Okay. And if that recipe is valid, if given any positive epsilon, the recipe applies and it tells us what the appropriate point is, then we know that the sequence is converging to the limit. The sequence can achieve any measure of closeness to the limit. If we just wait long enough and look far enough out along the sequence, we will see the whole rest of the sequence remain that close to the limit. So that's just translating the formal definition. Now I'm going to examine this, examine the left-hand side here. This absolute value, and oops, just rather than having it expressed as a absolute value of the difference, I'm going to combine those two fractions into one. So all that's needed here really is just the rules for subtracting fractions, or adding fractions, if you like. So this is going to be b minus bn. Yeah. And moreover, so there should be large absolute value signs around this quotient, around this fraction. But large absolute value signs around a fraction, you can simplify that down or reduce that down to the absolute value at the top divided by the absolute value of the bottom. Okay. And, well, okay, just to make it match exactly, we don't really need to do this, but we'll do it because it just matches how we write things in the definitions. That b minus bn, I can reverse around and write it as bn minus b, because, well, it's an absolute value. So all I've done is multiply that b minus bn by minus 1. I haven't changed its absolute value. So this is the thing I have to make smaller than epsilon. Okay. And as I said before, when you're trying to make a fraction of things small, well, you have to make the numerator small, but you have to make the denominator large. Or in other words, you have to prevent the denominator getting too small. So in order to make this less than epsilon, and by make it less than epsilon, what we really mean is find the point capital N after which this is always less than epsilon. That's what I mean. But we have this kind of feeling that we're making it less than epsilon. We're making it less than epsilon by finding the point capital N. So let's continue with this language. We have to make the numerator small. I'm just being imprecise about what exactly I mean by small, and stop the denominator bn, the absolute value of bn times b, stop this from getting too small. Because if that denominator gets very, very small, since the denominator of a fraction is going to cause the fraction to get very, very large. Even if we've already made the top small, if the bottom can get very, very much smaller still, that will still produce a huge quantity, so it will not be less than that. Okay, and here's where we start to make use of the assumptions. Okay, so first of all, I'm going to consider the denominator. Okay, so since Bn converges to B, and B is non-zero, I know that there exists a point capital N such that for all n bigger than or equal to this m, you can see what I'm doing here. I'm using the formal definition of convergence for the sequence Bn. Okay. Now I can find this point capital N that will make the absolute value of Bn minus B small, and I can choose that measure of smallness as small as I want. Okay. So I'm going to choose it so that the absolute value of Bn minus B, I'm going to insist that it be less than the absolute value of B over 2. So this is the epsilon I'm using here, absolute value of B over 2. And there's some point capital N such that at every point after that, this absolute value is less than absolute value of B over 2. So that's B plus absolute value of B over 2, and here is B minus absolute value of B over 2. Now why have I chosen absolute value of B over 2? Is everybody okay with doing that? Anything you're uncertain about that?
No.
Whereas the m? The m is coming from the definition of convergence for Bn converges to B. Remember, that's an assumption that we're making, where we are told that at the beginning, that Bn converges to B. So applying the formal definition of convergence to that, okay, I've chosen this positive number, absolute value of B over 2. I'm going to explain the significance of that in a moment. But I'm allowed for any positive measure of closeness of Bn to B, the definition of convergence tells me that there exists a point capital N, such that for every little n past that capital N, this inequality is size. So the existence of this point capital N comes to me from the definition of convergence for Bn converges to B. Sorry?
What's capital N?
Capital N up here is the point that we have to find which plays this role, which is a different one. That after that point capital N, this absolute value is strictly less than absolute. So our mission in this whole thing is to give a recipe for constructing capital N. But the existence of this point capital N comes to me from the definition of convergence, because this is to do with the convergence of Bn to B, which I'm allowed to assume. Yes.
Why is it B over 2?
Well, I haven't got. I'm about to explain that. Yeah. So why is it B? Well, why is it absolute value of B over 2? Remember, I said I wanted to stop. In order to make this quotient here small, I have to stop the denominator from getting too small. Because when your denominators get very, very, very small, close to 0, your fraction blows up. The reason I chose absolute value over 2 is because where is 0 in this picture? So you answered. You asked why did I choose absolute value B over 2? So you answer me now. Where do I put 0 on this in this picture on this number line? Okay, B is some non-zero number, so I position B here. Here's B plus absolute value B over 2. There's B minus absolute value B over 2. Where is 0 in that picture? Now we're a little bit uncertain because I haven't said whether B is a positive number or a negative number. But if I asked you to place 0 into that picture, where would you put it, or where would you not put it? That's the question.
At a distance B.
Okay, but I don't. Okay, but okay. On which side? Or we're uncertain. Okay, we're uncertain which side.
Yeah.
Okay, at a distance B, but we haven't quantified B. But in terms of what's there in the picture, where does 0 go, or where does it not go?
Within those bounds.
Yeah, see, 0 can't go inside there, right? Because I've chosen the size of this interval to be radius half of the size of B. Yeah? So wherever 0 is, it's either out here, if that's in the case that B is a positive number. 0 is over there to the left. Or if B is a negative number, 0 will be over here on the right. But the point is, I know 0 is not in that interval. Okay? Because the size of that interval is chosen carefully to be the absolute value of b over 2. We just use an actual number. Like if I choose the point 3 and I choose the radius 1.5, the lower value here will be 1 minus 3 over 2, 1 minus 1.5, which is equal to half. And the top limit will be 4.5. But the point is 0 is forced to be outside of that interval. Okay, because we've chosen the radius of the interval, half of the distance between the center point and 0. If I choose that radius to be half of this distance, I know I'm excluding 0 from the interval. So that is why I've chosen this. Okay? Notice that 0 is not in this interval around b. And so all of the elements of the sequence after the point capital M are inside this interval. So that means I can control the size of those. The ones inside this interval, they have absolute values that is less than the smaller of these two. And again, which endpoint is the biggest absolute value depends on where 0 is. If 0 is on the left or on the right. Okay, but I can just use the minimum of those two. So I'm able to control all the points in here. I can stick a lower bound on all the sequence elements that are inside this interval. And I know there's at most a finite number outside the interval. Okay? This allows us to control the size of these numbers, absolute value of Bn. If we let beta be equal to the minimum of, and I'm going to use minimum of the absolute value of b plus absolute value over 2, absolute value of b minus absolute value of b over 2. Sorry, I've changed the way I'm writing my b's there. Sorry, I went from a handwriting b to just a normal b. Sorry for the confusion. So I'm going to take the smaller of those two and the smallest and the minimum over all the absolute values of b1, b2, all the way up to b capital M minus 1. So these are the ones, these ones, b1, b2, all the way up as far as bm minus 1, these are the ones that might be outside the interval. I know everything past the point M is inside this interval. The point is, I'm now taking the minimum of a finite number of things. And we know that for all n bigger than or equal to 1, the absolute value of Bn is never smaller than beta. And beta is a strictly positive number. Because all these numbers here are strictly positive. Okay? And we're taking the minimum of them, so the minimum of a collection of a finite collection of strictly positive numbers is strictly positive. And because that beta is equal to the minimum of these, every element in the sequence has absolute value no smaller than beta. So that's why I was doing this, because now I can control the size of the denominator in my quotient expression up here. Because I know that this denominator never gets smaller than beta times b. So for all n bigger than or equal to 0, the absolute value of bnb is always bigger than or equal to beta times the absolute value of b. Okay. And that's a strictly positive number. then it could be extremely small. I could be forced to consider my quotient. I could have some very small things in the denominator. But the important, crucial part is I've been able to put a lower bound on it. I know there is some value below which the denominator in my quotient above will never go below. So now we apply the definition of convergence once more to the statement Bn converging to B. So we know there exists a point here's our capital N. There exists a point capital N such that the absolute value of Bn minus B is always strictly less than beta times the absolute value of B times epsilon. Okay. So the epsilon is the same epsilon that was given to me at the start of the argument. I know the sequence Bn converges to B. So that's one of the assumptions. I'm told that. So I'm free to choose this as my measure of closeness to the limit B. And I know that there exists some point capital N such that this absolute value is always strictly less than beta absolute value of B times epsilon, just the product of these three numbers. The reason I've chosen these product of these three numbers is now that when I divide this quantity by absolute value of Bn over B, this is always bigger than beta absolute value of B. So these two are going to cancel with these two above the line, and I'll just be left with the epsilon. So for every n bigger than or equal to capital N, if I look at this, so I started off looking at this absolute value. I rewrote this as the absolute value of Bn minus B over absolute value of Bn times B. That was the work we did a few moments ago. Rewrite this as this. Okay, so I can do it in some steps. First of all, I'll put in the fact that I know that the denominator never gets smaller than beta times absolute value of B. So if instead of my actual denominator, if I put a lower bound for the denominator, I know that the whole fraction is smaller than that. Remember, when you make the fraction small as small as possible, you're making the fraction as large as possible. When you make the denominator as small as possible, you're making the fraction as large as possible. And now I treat this thing on top, because I know little n is bigger than or equal to capital N, so I know that this is strictly less than beta over absolute value of B times epsilon over beta times absolute value of B. Okay? And that's just equal to epsilon. Okay. So that's what I've got across the page there. The bit I'm interested in is that this absolute value is strictly less than epsilon. Okay. If you look back to part 3 in the guidance, part 2 in the guidance sheet, this is what I declared that I have to prove. I have to find the point capital N such that this absolute value is strictly less than epsilon. Okay? And I found it. The point capital N exists because I got it from the definition of convergence for the sequence Bn itself. Okay? And it was based on choosing a degree of closeness of this beta times absolute value of B times epsilon, where the beta, okay, the absolute value of B is the absolute value of the limit of the sequence Bn, and the beta, remember, came from I was able to construct the beta as the lowest, as a lower bound on the absolute value of all the sequence elements. So that proves, this proves that 1 over Bn converges to 1 over B as required. So that's the special case. We've already argued that once we have the special case, we combine it with the product form we proved last time, then we know that the quotient form of the theorem is true for every pair of convergent sequences, An and Bn, as long as the Bn satisfies those non-zero conditions. So that's a nice proof. It's a good, decent length proof. It's not just really quick or really obvious, and it combines a number of things. We're using the definition of convergence in a few places, in different ways, and it also, which is good to see, shows some careful analysis of this kind of fraction. If you're trying to make a fraction small, the general principle is you want to make the numerator small, but you want to prevent the denominator from getting too small. Okay. Now you can get further help with this in your tutorials. Feel free to ask the tutors questions about this. The tutors know about this sheet as well. Okay. Any last queries about it? Okay, we've got about 15 minutes left. So some of the other, is everybody finished with that sheet? Yeah. We look shortly at some of the other questions on the tutorial sheet. So you have these initial ones about sequences. You have ones in the middle here focusing on the definition of convergences. So you've got these ones which are practicing applying the algebra of limits theorem to various sequences. Okay, we did an example of that last week. Skipping these ones for the moment, so I'm coming back to these ones up here at the top. Questions 12 and 13 are some more convergence results. So, like, questions 12 and 13 could almost be like a couple of theorems themselves, a couple of results in their own right. So I'm asking you there to think about how you might prove those using the definition of convergence. And then question 14 is a longish one. It's kind of like a little bit of a project to work on. And that relates back to this thing we did trying to estimate the value of pi in a curious way in induction week by dropping needles. So this is a far more rigorous analytic way to estimate the value of pi, and it corresponds more or less to how some of the ancient Greeks, so this is known as Archimedes' method for estimating pi. So this corresponds more or less to an exercise that ancient mathematicians were able to do to estimate pi. And it's to do with estimating the area of a circle by drawing the largest n-sided regular polygon you can fit inside the circle, and comparing that with the smallest regular n-sided polygon you can fit outside the circle. So those figures don't exactly match the circle, there's errors there. But as the number of sides increases, those errors shrink, and those errors converge to zero. That's the number n, the number of sides of the polygon gets larger and larger. And we can do that, we can make use of that to obtain a recurrence relation of quantities that converge to pi. And these recurrence relations are, I've called them quadratic in nature. The recurrence relation involves addition, subtraction, multiplication, and division, and the extraction of square roots. Now that's not too bad because early mathematicians were aware of rigorous methods to calculate square roots, and they knew about calculating square roots, and were able to calculate square roots, more or less as accurately as they could be. So that's kind of like an extended project or an extended piece of work for you to do. And so I very much suggest that you have a go at that as well. then what I want to come back and talk about now are these questions 8 through 11. So these are, well, 8 through 10 anyway. These are applications of the monotone convergence theorem. Now, we haven't said that much about the monotone convergence theorem up to now. So this is the theorem 1.3. We can have a look at it in our notes. We did talk about it a little bit earlier on. So the monotone convergence theorem, it's not something we're going to prove, and proving it requires you to consider what the real numbers are very careful and in detail and how the real numbers are constructed. We can consider it as just like a property of the real numbers. And in some sense, it's kind of like a defining property of the real numbers. It's a characteristic property of it that kind of contains the essence of the real numbers in it. But what it says anyway is, it says every bounded monotonic sequence is convergent. Well, we know what a bounded sequence is. A bounded sequence is one which never strays beyond certain limits on the number line. It's contained in some size of interval. Monotonic, remember that a monotonic sequence is one that is either increasing all the time or decreasing. So that tells you that if a sequence is increasing all the time, and if there is some upper limit to it, then it will be a convergent sequence. Okay? So the MCT, just the main idea. I mean, clearly, if you've got a non-bounded increasing, okay, there's a quick sketch of a non-bounded increasing sequence. It's some kind of process, it just keeps getting larger and larger, and there's no upper limit to it. It's just going to keep on going up and up. Okay? It's not hard to see that this might not be convergent. Okay? If it's going to be increasing and it's non-bounded, there isn't some final limiting value that it's getting closer and closer to. It's just zooming off to ever larger and larger values. Okay? But if you've got a bounded increasing sequence, so there's some, there is some upper bound beyond which it can never go. But this is the bound. Well, if my sequence is increasing, you see, I can't just zoom it off to infinity because it can never go beyond this. So maybe it could start to level off. You see, the upper bound forces it to level off. Now, we're not saying that it definitely has to converge to this quantity, but the presence of the upper bound and the increasing nature of the sequence means it can't be wobbling up and down. I mean, if it could not converge if it just wobbles up and down forever, then it's never getting closer and closer to some final limiting value. But it can't do that because it's increasing. Well, the presence of this upper bound means there must be some number smaller than or equal to the upper bound, and the sequence must be converging to that number. Okay? So the MCT, the monotone convergence theorem, implies this sequence must converge. And the fact that there exists a limit in the real numbers for any sequence like this, that's kind of characteristic of the real numbers. It's not a property enjoyed by rational numbers. You can quite easily construct increasing sequences of rational numbers that don't converge in the rational numbers. Okay? They still really are a convergent sequence, but their limit is converging to a irrational number. Okay? So the limit isn't necessarily contained in the rational numbers. The real numbers kind of contain all the quantities on the number line, so they're complete in that sense. So a bounded monotonic sequence will always be convergent. But we can use the MCT. And we can make use of it in situations like, for instance, question 8 on the number sheet, on the question sheet. So question 8 asks you to consider this sequence here. So it begins with root 2, then it's the square root of 2 root 2, then it's the square root of 2 times the square root of 2 times the square root of 2, then it's the square root of 2 times the square root of 2 times the square root of 2 times the square root of 2. And if you continue it on in the suggested way. So each time you take what you had before, you multiply it by 2, and then you take the square root of the whole thing. Okay? That's the rule for generating the next element of the sequence. Now, okay, this looks like a rather funny, curious sequence, but we can analyze it with the help of the monotone convergence theorem. So how do we do that? Well, there's a few steps here. First of all, it says formulate this as a sequence defined by a recurrence relation. Okay, so we got root 2, and we multiply the previous element by 2 and take the square root. And we multiply the previous element by 2 and you take the square root, etc. That's the rule. Okay. So as a recurrence relation, this can be written as the sequence xn, say, where x1 is defined to be root 2. So for a recurrence relation, you have to get it started by supplying the initial value, or a few initial values if necessary. And then after that, the rule is xn plus 1 is when you multiply the previous element by 2, and then you take the square root. Okay. So that's a recurrence relation. So recipe for constructing the sequence, which tells you how the sequence starts at the beginning, and then tells you that each term is some recipe of the previous term. Okay. Square root of 2 times the previous term. Now we want to apply the monotone convergence theorem, so we want to prove a few things. We have to prove that it's bounded and monotonic. Now, if you look at a computer plot of this, what you observe, if you plot out the first few hundred values, what you observe is that it's an increasing sequence, and you observe this getting close. It seems to be getting closer and closer to 2. So that you can get a good idea just from experimentation of what's going on. But it's a different matter to prove that. Okay? So certainly we can say it's bounded below by 0, i.e. xn is always bigger than 0, as we only see positive quantities involved. Multiplying together positive quantities and taking the square roots of positive quantities. Well, okay, if we're taking the positive roots all the time, then everything is positive. So certainly all elements in the sequence are bigger than 0. Also, we can say that the sequence is bounded above by 2. So we can prove for all n bigger than or equal to 1, xn is always less than 2. Certainly it's true, certainly x1, which is equal to the square root of 2, that is strictly less than 2. And after that, xn plus 1, which we can write as the square root of 2 times the square root of xn, well, you see, if I already know that xn is less than 2, this will be strictly less than the square root of 2 times the square root of 2, which is 2. Yeah. See, this is an example of a proof by induction. This is using the fact that xn is strictly less than 2. I know the first one is less than 2, and then if I assume the previous one is less than 2 here, because I replaced xn by 2 here, I then get that the next one is less than 2. So the sequence is bounded above by 2. Okay, just got to wrap this up too. Bounded above by 2. Also, the sequence is increasing. Since if I have xn plus 1, okay, by definition, that's the square root of 2 times the square root of xn. But this has to be bigger than the square root of xn by the square root of xn. Why? That's because xn is strictly less than 2, but of course that's just equal to xn. Okay, I've already proved that the sequence is bounded above by 2, so this shows that xn plus 1 is strictly bigger than xn. So it's an increasing sequence. So the monotone convergence theorem tells me there exists some number x such that xn is convergent to x as n converges to infinity. Okay? It does have a limit. Then taking limits of the recurrence relation, so if I take the recurrence relation says xn plus 1 is the square root of 2 times the square root of xn. If I take the limit of both sides of that, the limit of xn plus 1 is equal to the limit of the square root of 2 times the square root of xn. Well, on the left-hand side, we've got the limit of the sequence, so this is the quantity x. On the right-hand side, we've got the square root of 2 multiplied by the square root of xn. Using the limiting properties of the square root function, this will be square root of x, because xn is converging to x. We can square both sides. We get x squared is equal to 2x, and then divide across by 2, so we get x equals 2. So that shows you how, for an example of looking at a certain sequence, investigating it, we can see increasing bounded behavior, it seems, when we look at some initial part of the sequence. We can then prove the bounded increasing nature of it using an argument like I've given there. Then what that tells us that the limit exists by the monotone convergence theorem. And knowing that the limit exists means we can analyze the recurrence relation. The limit itself has to satisfy the recurrence relation, and then we get an equation for the limit, which we can then solve and determine, prove what the actual value of the limit is. Okay, so there are a few other questions like that which require the use of the monotone convergence theorem left on the sheet there. Yeah, I'm sorry I didn't get to introduce the series topic, but no harm really. It means my 2 lectures next week. So we'll begin chapter 2 on series, and we'll get that started. Okay. So, okay, thanks for listening, everybody. If someone could just bring down the signature sheet. Anyone else that available? Thank you. If you didn't sign it, it's down here.